This is not a video of my telling you some absolute truth. I take you through what I understand as of this recording. If you believe my understanding is wrong, please explain why in the comments. Also, look to the description where I will put in corrections if needed. Before I get into the weeds, my simple argument is that it doesn't matter how many ADCs are in this device. I say, from an engineering perspective, there is only one. It doesn't matter what memory space it writes to, assuming there's enough space for all the signal's data. All that matters is if we can play back what we recorded to match the kind of sound we're looking for. If you just want usable audio for a podcast, corporate interview, vlog, that recorder will work fine. Everything important is in auto mode. But this device only gives you one choice of noise to distortion. This device, for example, gives you many choices, and some of them can be bad. And let's see if I can get some focus here. There we go. Or I brought out this device, which is still very usable. Again, has many features that the other device does not have. And I just have to, there we go, I just have to get focus on it. Let's imagine a spaceship lands on Earth. You're going to have to excuse my artistic skills. The spaceship lands on Earth. And of course, humans try and open it in just every way they can with lasers and even with nuclear bombs. But anyway, none of it works. And then one of them notices there's a little hole in the spaceship. And from the spaceship comes a little stream of water, a very small stream of water. And some of the tinkerers, the scientists, analyze the stream of water, and they say, I think it goes in like little waves. Maybe they're communicating to us through this very small stream of water that we can't see the waves in it. We don't know what to do with it. So what are we going to do? And the tinkers say, okay, well, we need to amplify this little stream of water so we can see the waves, and maybe they're communicating. So they build a device, and the device in a very, the first part is that it's basically another tube of water. So they feed water, right, but it's a lot of water compared to this. And then there's a little lever. And the little water from the spaceship comes and it hits the lever, and the lever will move back a little bit. And as it does, this water will come down into this large tube. And they notice that as the little water hits it back, that it pulsates back and forth because it's like little waves, they'll create bigger waves in the bigger thing of the water. And then they'll actually do this again. They'll take this and they'll have another big thing of water, and they'll hit this, and then the waves will get even bigger. And up they do. So that's how they amplify in the water. And as the water is amplified enough, they can see the waves. They can see the waves coming out of the ship. Whereas before, it was just like this. They couldn't really see it. Now, I want to point out, I want you to imagine this in your head, because this is certainly possible. You can imagine water. You can imagine water in pipes and little levers to allow a lot of water to go through based on how the little water pushes it. And this is basically, so if we talk about microphones, of course, this is the input, right? Input voltage, or the source signal, right? And this is the output voltage. So this would be 5 volt, let's just say, from your battery or whatever. And this is a basic way that preamplifiers work, which are just another form, just amplifiers. This is the way they work for the microphone signal and for this spaceship. Now, remember, think about the water. So the water hits the lever, it's gone. Like it goes away. It doesn't have its waves anymore because all the energy of it is used to move this lever. Now, in electronic transistors, it's a little bit different. It actually becomes part of the stream, but you could actually imagine it in this case. They would hit the lever and then would go into this bigger stream of these waves. And then these waves would go into this and go into this bigger stream of waves, right? And going up and down until you get to the waves are so big that essentially it's very actually easy to copy them through this other sort of lever system, or whatever you want to call it. So yeah, this is the basics of amplification. The main thing to remember is every time when you're amplifying something super, super small, whether it's a little stream of water or a little microphone, depending on the materials that you can build these things with, it leaves once you do it. You can't go back and re-amplify it again. It gets consumed in the amplification process. And microphone voltages are so small, there's no way to do this like just in one step, or just to split this into like two streams, just like you can't imagine splitting the water into two streams. Okay, so we're now going to switch to mics. So we have our mic, the very small microphone voltage, and it goes into, let's say I'll hit a lever in here, but it's not really a lever. The transistors work a little bit different, but whatever. I think to think of it mechanically is a little bit better. And this voltage comes in from the output, and it creates a signal. This signal goes into another lever, and that goes into another lever. And that's basically how modern amplifiers or preamps work. It's basically, these are all transistors, and the source signal, or an input, will hit the base, or hit basically, in a sense, the lever, and current coming outside that's regulated will get bigger and bigger. So even though you're starting with a small little thing, at the end you get a big waveform. But remember, this is gone one time's use only. All right, so when they did this, I do need to go back to the spaceship example. I'll say we're back to a spaceship, but we can actually just think of this actually as a little small electrical current, like a microphone coming out of it. And we have a whole bunch of transistors that builds up the signal, but let's just assume that it's just done with one transistor. So it comes in and it creates this signal. But we notice as it's creating the signal that it's clipping. Like, we think there should be more here, because actually it's amplifying it too much that this is happening. And then somebody says, okay, well, we have to decrease the amount of voltage going into here. And as we do that, because there's less voltage to amplify, these things become smaller. And now we can see the whole wave, right? So we've reduced remember, we're doing nothing with the voltage coming from the spacecraft. We're only doing the voltage that we used as part of the output amplification. So as we reduce that, we now see that. So we're pretty happy, right? And we can listen to it, and we're listening to it, and it's like, oh my God, there's an alien. Yeah, that's an alien voice on board that we're listening to. And sorry for the bad alien image. Okay, so we're listening to the alien, but then somebody says, hey, but I hear I think there's another voice there. I can't really hear it. So I heard it more in this one, right, than in this one, version B. Version A, where we're sending basically only, let's say, 1 volt through the output to create the output, and B, where we're just sending actually half a volt, let's just say. So we're seeing less, but we heard more here. So they said, okay, let's do a third one. And the third one, right, let's go down here. In the third one, we're going to do 2 volts. So even though we get clipping, we hear a signal in here. And we realize, oh, there's 2 aliens in our ship. There's a little alien with a very small voice, and there's a big alien with a big voice. And if we put the output voltage through our amplifier, if we put a little, then we can hear the big alien. If we put a lot more, the big alien clips, right? But we can hear the little alien. And that's the exact problem that audio engineers face. The materials we have, the earthly materials, the human materials, we don't have this super technology that they have, though we don't know that they can even do it inside. Using the materials we have for our amplifiers, whether we're amplifying water or we're amplifying electricity, they won't perfectly take a small signal and amplify it perfectly. it's a function of how much leverage we can get between that and each little transistor or amplifier. And just based on the way this stuff works, we can't get the whole thing. We sort of have to pick what part of the signal we want to amplify to get, some good fidelity. Because for every amplifier, there's a point at which the linearity breaks down, and that's sort of why you get clipping. And then there's a problem where if it's very low, then you get noise. So even when if we do 2 volts, like when we're getting something, and let's just say we're hearing the alien here, right? We're still going to get a bunch of noise here, right? Which we don't want. So it's, you have to pick what trade-off you want. You have to pick what part of this signal that you want to get. And that's why you have a gain knob. The gain knob is up here, and this allows you to set how much voltage, whether you want to get the louder sounds not clipping, or whether you want to get the smaller sounds up, assuming that you're not going to have clipping. And that's the way it works. So I needed to go through all this because it's very important for the next step when we talk about the ADCs. Right, we've taken our input signal and we've amplified it, and we have our signal. Now, on a microphone, it goes back and forth, alternating current, but we're just going to consider it as DC for the simplification here. So we have our output from our preamp from a microphone, and we have this. And what does an ADC do? Well, let's just imagine like a little person in here, right? So it was needing a bigger head, right? So it's a little person. And what they do is every 48 thousandths of a second, they can sample in different rates. Every 48 thousandths of a second, let's just say, they look at where this amplitude is. So here they might mark it as a 5. And here it might be, a 10. And then here it might be a 12. And that down here it might be a 2. And then up here it might be, 250, right? So every 48 thousandths of a second, they're looking at this and they're figuring out what that number is. Now, how does this happen in the circuit? And we can even explain this even using the water thing. So let's just say, getting back to our water analogy, we have water that's been amplified from a spaceship that's coming in. So what happens is every 40th of a second, it goes into this waterfall. Now, there are many ways of quantizing voltages, and they have some very sophisticated tricks. But this is the simplest, and in a sense, I feel they're all sort of like this. They're all sort of based on these weights. So, and the way they do the weight is they have a bucket at the end of each one, right, that will hold a certain amount. So it comes, the wave comes through, and let's say the first one, it fills up this bucket, right? And the second one fills up this bucket. And let's just say that these buckets are, in digital, 1, 4, maybe 2, 4, 8. I'm screwing with the math here, but you get the idea. So it'd be 8 plus 4 would be 12. So this would be a 12 because it fills those buckets. It compares. And so in a comparator, essentially, and this is something also very important to understand, is that everything in analog to digital conversion is always, almost should be called like analog weights to digital. I mean, because each analog pressure or voltage, or if you think of it as water, is compared to a weight. And this weight says, oh, well, it's at least, it's at least 8. And then this weight, just like imagine going to the doctor and doing a scale this way. This weight's a 4. And then, okay, and the 2, well, we don't get anything. So it actually, right, we go this way first, right? First look on the 1 and then say, okay, I got a 1 here, right? So it basically just takes successive weights of the voltage and then adds them up for whenever a weight is met. It's compared to the weight and it matches. That's why it's called a comparator. Each voltage is compared against successive other voltages, which are weights, and when they match, they tally up what matches into the final number. So that's how this basically works. So how does a dual ADC work, right? Because this is one ADC. analog to digital converter. Now, again, I don't believe there's any such thing as two ADCs or multiple ADCs, because this is a generalized term of you take an analog and you're converting it to digital, right? And it doesn't really, it's not like a discrete component. It's a collection of lots of transistors and capacitors and diodes and whatever, right? I mean, it's a complex thing. So to say you have two different complex things, anyway, I'm going to leave that alone. Anyway, so we have our one ADC, and he's capturing these numbers every 48 thousandths of a second. So what sound design has said they're going to do, or their theory and their patent, is we're going to take this signal and we're going to duplicate it. Now, they don't say they're going to duplicate it, and that to me is misleading. I mean, I think if you're an electronics engineer, you understand that's what they mean, but this is where it confuses like many YouTubers or stuff like that. But anyway, so they have one ADC, and now they're going to create another version, another copy of this. And let's just say also, I'm going to extend this a little over, that this one has some clipping in it, right? So what they're going to do is they're going to take this copy and they're going to create another copy, let's say negative 20 dB. And in this copy, of course, it's going to be smaller because they're attenuating it down than the other one. But this one won't clip as far as the ADC is concerned, right? Because there's still plenty of headroom between where the signal ends and here, right? Because actually there'll just be a line here. So what Sound Devices is saying is that, okay, so we have the second ADC. We have this person here. So now we have another person, like another ADC head, and they're also writing down these numbers. And this guy is really going to focus on the lower numbers, and this one's going to do the higher numbers. So when he looks at here, he doesn't see 250, he sees 251. And they're saying, okay, he sees 251, and this guy saw 250, but this is more accurate because he's just paying attention to this. And the question is, right, is how different are these two numbers? Like, what difference do they really make? Like, you can't really see more dynamic range because it's clipped. Whether this clipping here is here or there, right? Whether it's that number or that number, the number stays the same. It doesn't make a difference. So whether they're all at 251 or 250 or whatever, doesn't make a difference. But anyway, that's their claim, that if they use multiple ADCs, taking the taking the output from the preamp and making copies of it, and then analyzing each copy based on frequency or amplitude or whatever, that they can come up with a set of numbers that give you more dynamic range. How is that possible, right? Because the dynamic range is baked in with the original output voltage. You can't create data that isn't there. I mean, this is Shannon's law, right? So how are they doing it? So, but, you could say, well, hey, maybe the ADC homunculus man that focuses on little ones and the one that focuses on big ones can somehow read them better and give you better numbers. So I can see how this, I guess, supposedly could work for more resolution, let's just say more accuracy, but I don't see how it works for more dynamic range. So to me, it's really, it's a theory, but I haven't seen it in practice. And anyway, I just want to go through this so you understand what they're doing. They're not taking the original. This is a point I make over and over again to people who comment on my videos. Sound Devices, no ADC, no audio interface, takes the original microphone voltage and splits it up into separate voltages that it applies an ADC to. It's impossible because this voltage is too small. If you don't believe me, please just ask Gemini, Claude, ChatGPT, whatever. Say, can a microphone voltage from condenser or dynamic, can it be split up into copies that are the same fidelity as them all? No, it can't. You would destroy the waves in them, essentially, the signal. So anyway, it takes this and it puts it into one line level, essentially. So line levels, let's just say it's 1.2 volts, right? And once it gets to 1.2 volts, you can copy it many times. But how can you copy something and get more information out of it? Against Shannon's law, right? All the information is here. So the question is, okay, well, you're now saying that somehow you have multiple ways of looking at this and you'll get more information. Again, to me, breaking Shannon's law, but whatever, okay. So you say that these different electronic circuits can get more out of it. How would they get more resolution? How would they get anything? Now, what they get, I believe, anyway, I don't think that they really get much. And we're going to go to the spec sheet of the chip that Sound Devices probably uses in their equipment. Now remember, Sound Devices, Zoom, Tascam, none of these companies make their own chips. They basically just take chips from foundries and they add firmware and other electronics and they build these audio recorders. But they don't build any of this. They don't build the preamps chips. They don't build the ADCs. You know, they might do some of the stuff in the preamp, but basically all this stuff is basically off the shelf. So we can go look at the off-the-shelf spec sheet and see what is really happening compared to that claim that they're saying, okay, multiple ADCs is giving you more headroom removing clipping. Again, I don't see how it can remove clipping because, again, the clipping is there. It's here, right here. You can't recover this information just by dropping it lower here. That just won't happen. So anyway, let's move on. Okay, so here's the, blanking on their name. Anyway, here's their AKM 557 series ADC chip. And if I asked, Claude AI and these other, and they basically said this is a chipset they believe Sound Devices is using in their equipment. Anyway, this document is from 2022, so I think it's as modern in ADC as you're going to find. And what it says is saying, okay, it's differential input AD converter for digital systems, and it says 121 dB of dynamic range. Now, since you need about 6 dB per bit, that is 20 bits, right? So 20 times 60, right? Sorry, 20 times 6 is 120. So this equals essentially 20 bits of information. And, an audio engineer will understand this. He understands, okay, it's 32-bit, but so you're only getting 20-bit. And if you look at 112 dB, if you're looking at that as a measure of signal to noise, right, not 21-bit, then it's more like, what is this, more like going to be, 18 or 19 bits. Again, this is theoretical max. So it integrates 2-channel AD converter, blah, blah, blah. And then it says the, okay, so down here, I'm losing my map. The channel summation mode, right, improves dynamic range preference by summing up multiple channel analog to digital data and averaging. So this is the multiple ADCs that Sound Devices talks about, or all these YouTubers talk about. This is what they mean, multiple ADCs in a sense. But they're not calling them multiple ADCs because just like me, and I think most people are like, listen, ADC is the whole general thing we're doing here. So if we do multiple ADCs in this documentation to engineers, it's like saying to engineers, hey, we have an ADC that has multiple ADCs inside it. They'd be like, that doesn't make any sense, right? Is an ADC of multiple ADCs? No, it's not ADCs. There's an ADC of multiple channel, right? Channel processing. So it has multiple channel processing, and the dynamic range is improved to 124 dB in 2-to-1 mode, right? So that's where it's taking the two ADCs and it's basically picking the numbers, as I showed you before, of the analog output from the amplifier and putting those numbers in it. And so the difference between 124 and 121 above is 3 dB, which is a joke. Because the microphone, if you look at a microphone specs sheet, most of them have usable signal to noise of 86 dB or something like that. I mean, yeah, some of them have 120 dB, but if somebody actually screamed into a mic at 120 dB, they'd be blowing your ears out there and when you play it back. So no microphone is going to get even close to this. In fact, most microphones, I would say you end up working with 60 dB because of the noise that comes from the microphone, the preamps circuit, just in the room and stuff like that. So in the real world, since you're never really going to go above, in my opinion, 86 dB. I think it's everybody's opinion, 60 dB, whatever. But even even if you take them at face value that yes, we need 121 dB of dynamic range from the microphone, that we're going to use all that, like an extra 3 dB is just nonsense. And so anyway, let's look at more of the this document. Okay, so we're looking at the sound devices patent, which again doesn't represent anything that necessarily works, right? They're just saying they have this thing that's going to work. So here you see it says analog input signal source. Now what they mean here is from the amplifier or the preamp. It is not the microphone source. And any engineer who looks at this is going to understand that, right? Okay, so they're taking the signal from the microphone after it's been amplified a whole bunch. They're taking this and now they're doing a lower gain stage, right? They're taking the analog gain. And you see this word here, filter? That's very important. You know the same here, filter 2 and filter 3. So the filter 3, you're now talking about digital essentially, right? So you're doing digital work here. And what happens is it goes to this ADC. Each one of these creates a number of what it sees in a waveform at 1/48th of a second. So let's just say this might see, 200, and this might see 201, and this might see, 199. Then all this logic right here, see these window functions? What the window functions do is they look at these numbers and they say, oh, this is the best number. We're going to put this one into the final output. Remember, an ADC is just an overarching name for taking analog voltages and converting them to numbers. So it's going to say, okay, we've taken the already amplified from the microphone, we've copied it 3 times, and then we're going to analyze each one that is the same but has a different filter on it based on frequency or amplitude or whatever. Again, it's the same data. You can't fight Shannon's law here. And we're going to look at it, and through our new method, we will get better numbers here, and we will put them there. But again, how are you going to fix clipping this way? You're not going to get any more data. Now, you could maybe fix clipping. So let's just say, you have a wave, it's coming down, right? And let's just say that it just barely clips. So you could say with this method, oh, well, normally if we put it through, this would have been 201, right? Let's just say, well, let's do it in 8 bits. So this is a 256, right? And this one, instead of 199, let's say it was 252. So normally, yeah, it would have clipped because if we just did it straight without a multiple whatever, 256 would have clipped here. But because we used this multiple ADC, we know that it actually just, it went like this. So it didn't clip. But just barely at the top of the waveform. I suppose you could make the argument, yeah, okay, you've sort of extended the dynamic range because with a single ADC, again, this is a whole complete ADC, this is nonsense of the multiple ADCs, but whatever. If you're just using just what this old fake method, that you would have gotten this, and now with this method, you're getting this, right? So you didn't clip. So you could sort of say you got more dynamic range. But it just, this is not there are no electrical circuits here. This is basically a back of the napkin, theoretical thinking. So here, if we look further down, now these are, I'm not going to orient them, but this is basically they're showing, okay, this is what we get with one ADC, and if we had a second ADC, we could use this, and we'd get more, right? We'd get more resolution or less clipping or whatever. But none of these charts and graphs, as sort of sophisticated as they look, they're not talking about any data. They're not talking about how they generated it, right? They're not saying, oh, we took this signal into our device with these chips or whatever, and this is what we got. That data is all made up. There's no real voltage type data. They're just formulas, right? Formulas for like, okay, well, if we had a certain type of signal here, and we put them through these matrices that we can get. So this is just all math, but there's no electronics whatsoever in this patent application. But if we go back to the data sheet, which is what engineers have to use in the real world, you will see that there's tons of information about voltages. So let me just go further down, because this is mostly just how it right. There's all stuff like, okay, your power supply, it's got to be minimum 3, maximum 6 volts, right? That's it. And I want to warning: operation at or beyond these limits may result in permanent damage to the device. Normal operation is not guaranteed these extremes. So everybody says, oh, well, it can fix clipping because 32-bit float, you can get clipping. Again, we already know the max voltages in every discrete part of the component that's allowed. If it tries to generate a voltage above that, it will get clipped. I mean, the system will clip it itself, because if it doesn't, it will result in permanent damage. So either the electronics engineer has to make sure it never gets more than 6 volt, or hopefully in the device itself, it would have circuitry to say, okay, this is old, we're just clipping this, we can't deal with it. Because again, all these things have, anyway, the point is, look at this, minimum voltages, all these voltages and these power supplies, the reference voltage, what comes in, what it has to deal with, it's all very specific here. It's not that made up stuff in the sound devices. And when you're looking at this, right, it's showing, like we know, okay, it's sending in probably a 1 kilohertz tone, and now it's showing what happens to that signal as they record it. Again, because we have all the voltages, we have all the numbers, we have all the specifics. But none of these charts mean anything in the real world of microphone recording, right? I mean, they can show improvements here, but it doesn't mean that that's an improvement that you would ever notice recording a microphone. And of course, you'd need to be pretty sophisticated to know whether it has anything to do with it. Now, this is all just about timing and how the data moves about from this chip to the rest of the circuitry that you'll build around this chip. But I just wanted to point out that, again, if you look at the actual chips that supposedly have these dual ADCs that Sound Devices is talking about, I see no indication that they're borrowing from the tech patent or anything like that. You will see that they're not really dual ADCs. It's just digital processing. They're copying the signal. It's an exact duplicate of the signal. It has no more data than the first signal, Shannon's law. And all they're doing is digital work. They're basically saying, okay, let's just try and predict what was probably should have been here. Let's predict what is noise. And that's really I would say that's the two things that that these ADC chips will do. So the ADC modern chips will try and digitally do two things. Again, can't do anything with the analog signal. They'll take the analog signal, and they're going to have two types of filters, right? They're going to have a filter that's going to try and take out noise, right? So if there's noise, the filter is going to try and take out the noise. If there's clipping, right, the filter is going to try and make up where that data, they think the data was, where it was going, put in some of these things. And that's what the two filters do. So modern ADCs. And yeah, you could call it like multiple ADCs, but if you look at some of these spec sheets like before this one, they just talk about the filters. They don't even talk about multiple ADCs here. Like I pointed out before, I talk about multiple channels. But everybody knows it's the same thing. There's only one ADC, and the ADC can use all kinds of techniques to come up with its number. Because remember, it's analog, right? It's analog, right? Digital, analog to digital. It's just to a number, right? Say the number 7 or the number 42, right? That's all it does. It takes a voltage, do circuitry, and it comes up with these two numbers. How it does it in between it, right, has all kinds of tricks. But you have to understand what kind of tricks it's doing. And when these tricks are talking about, they're just computational. They're not actually extracting more information from the data.